we know, unfortunately, is that the likelihood ratio, the chi-squared test that we ran, is extremely sensitive to sample size. So I've got to be careful about rejecting this simply based on this number alone. I've got to be careful about rejecting this simply based on that number. Because it could be that that's overinflated because it's too large based on the sample size. Now, that's why we look at the other pieces of information. So let's talk about let's use the CFI and the TLI first. These are what we call our standard goodness of fit measures, and they're structured to be like an R. 1 is better, 0 is bad. So we notice that the closer we are to 1, the better these are. The general rule is 0.95 and above is considered excellent. 0.9 and above is considered okay. 0.85 and above is kind of iffy. Below 0.85 and it's really questionable. So in this case, based on just the CFI and the TLI, 0.98, 0.96, these appear to be pretty good. Now, the chi-square is the gold standard. If the chi-square is significant, I don't care about the others. My model fits statistically. But in this case, the chi-squared doesn't fit, so I move to other assessments. The SRMR is 0.018. SRMR is generally, we use the cutoffs of 0.05 and 0.08. SRMR and the Ramsey, the RMSEA, are both badness of fit measures. So you want those to be small, you want your goodness of fit measures to be large.
Sorry, you said the cutoff is 0.05 for SRMR and 0.08 for RMSEA?
No, together they're both actually. They're both 0.05 and 0.08.
Do you want it to be higher than the 0.05?
Nope, you want it to be closer to 0.
Okay.
So as a measure of badness of fit, so I'll do the SRMR first. SRMR is 0.018. We want that to be less than 0.05 to get excellent status, less than 0.08 to get a reasonable status.
And you said that the chi-squared is actually more vulnerable to larger sample sizes.
It's sensitive to sample.
Yeah, it's sensitive. But you'd think they would be more accurate with larger sample size, but actually
remember, it's
it has more information to sort of deviate from the model almost.
It's overly sensitive, so even the smallest amount. So with
you have an extra 10 data points instead of
well, it's more that the chi-square distribution itself is sensitive to small changes.
Okay.
So a small change, so if it's off by 0.1, we might say, oh, that's pretty close. But technically 0.1 isn't 0. And it's going to say that. And the larger your sample size, the more attuned it's to saying that that's. So again, 0.05 and below is good. It's excellent. 0.08 and below is good. And it's pretty much the same rule that we use for the Ramsey, the RMSEA. Now notice here, the Ramsey is 0.131, not, not less than 0.05, and definitely not less than 0.08. And SEM Stata actually produces what we call a p-close. This is the probability that the Ramsey is close to 0.05. Well, it's the probability that the Ramsey is less than or equal to 0.05, and we randomly got 0.131 is 0. So as we're really nowhere near 0.05, so we might be closer to 0.08, but even there. The 90% confidence interval is only 0.115 to 0.148, so we're probably not very close. So chi-square test says it's not good, but that's non-common. Right? Ramsey says, it's not good. CFI and TLI say it's good, and the SRMR says it's good. So what I want to focus on right now are the types of hypothesis tests that we can actually run. I can't run a hypothesis test with SRMR, TLI, or CFI. Technically, I could run one with the RMSEA, but that's only to tell me if I'm within the range. And the chi-square test that I ran essentially says reject the null. But remember, the null is sigma equals sigma dependent on theta. That's the null. If that's wrong, if we reject it, then that says our population doesn't equal the model. And if we, oh, sorry, it's going to go to the save screen. So it's going to give us the, so it says, according to this, that we would have to reject that. We don't really want to do that out of hand because we know that chi-square is sensitive. All right, so let's take a look. So now again, what we're going to do next is let's look at the standardized values. So I'm going to type SEM, comma, standardized. It's going to take my output. So all this does is take the last set of output I ran and standardizes my values for me. So I want the influence, the measurement model has a coefficient of 0.85, 0.80, 0.86, 0.92, 0.86 and change. And what we know in the standardized perspective is this essentially tells us how correlated these values are, these measured items are, to that construct that I can't actually see. Now, this is another rule that we can sort of go back. From EFA and CFA rules, generally we want standardized factor loadings of 0.7 and above. 0.6 is probably okay if there's not too many of them. 0.5 is not ideal. And 0.4 is really pushing it if you have more than 1.4, and below 0.4 is bad, and 0.3 is generally considered not acceptable at all. All right, so we're nowhere near the 0.4, 0.5, 0.3 cutoffs. In fact, our lowest value is 0.8. Now that seems to suggest that there actually might be, so that seems from a factor perspective that we actually may have an okay model, and it's just the case that we were off by a consequence of sample size. Sorry, my brain, there's like 6 or things going there, and I was trying to keep track of all of them. The sample size is probably one culprit. Now, what you're going to learn is, as you start doing a number of these, you're going to start to realize there's certain things you can look for. Now, as a consequence of the Ramsey being off, but everything else being good, that's a clue that you might actually want to take a look at your modification indices. So let's talk very briefly about modification indices.
Quick question.
Yep.
Are there specific people / articles that are a good reference for these cutoffs?
Hugh and Bentler. H-U and Bentler. And at some point I will come and talk about those a little more specifically. But I want to practice with them before we go and start to see how some of them are more useful in some ways than others. I think that's a good way. So you'll find that you'll be drawn to some more than others. All right, so what I'm going to do is I'm going to run the modification indices. Here, so E stat M indices. All right, so let me scroll down a little bit. So I want E stat M indices. Okay, so here's the code that I just ran. Okay. Now, the modification indices are known. The modification indices are known as, another term that you'll see is the Lebrons Multiplier, LM. So the Lebrons Multiplier is this nice little tool that we have for multivariate calculus that says, if I want to look at something carefully, I have a thing that's existing in multidimensional space, I could change any one of my predictor values, and when I change that value, I'm going to see a change in the dependent variable that I'm focusing on. Well, that just works. There's multiple dependent variables, but gives me a measure of the change. And the Lebrons multiplier is this wonderful little matrix that essentially says, look, if you do this one thing across the board, it will tell you what would happen if you change any one part of your model.